Great. Good morning, everybody. Welcome to the NSF OOI Cabled Array Program webinar. My name is Brian Iddig. I'm the Program Manager here at the Cabled Array. We're glad you're here today, and we're excited to talk with you about the cabled array and potential opportunities to connect infrastructure to the array. I guess today we'd like to present an overview of the cabled array and then engineering specifics for connecting, communication, testing procedures, and general timelines. I guess for procedures for today, if anyone has questions, we can just answer them as we go through the slides. That'd be great. Also, in addition, the cabled array team is available for one-on-one meetings. After the meeting, we can set up a specific time to answer any additional questions. I think sign-ups are available through the website. Again, I'd like to thank you, and we'll start the overview presentation with Deb Kelly.
Great, thanks. Yeah, so I'll just do a overview of what's in the water right now and provide some a summary of what kind of data we can make available to that are available to PIs that are interested in adding infrastructure, and then a little bit of the process, and Dana will go into more of the testing, integration, and requirements. So all this information is on the OOI, oceanobservatories.org website, and a lot of it is on the Interactive Oceans UW educational website. The primary infrastructure, there's two different kinds of infrastructure that we talk about. The primary, which I'll show you some more images of in a minute, it was designed, constructed, and installed by LT Ameripro. It includes this 900 kilometers of telecommunication grade, but much higher power than normal underwater cables that go from Pacific City, Oregon, across the Juan de Fuca Plate out to axial seamount, and then another line that heads south along the subduction zone and into 80 meters water depth off Newport, Oregon. The orange red boxes are primary nodes, so you can think of these as large substations on the seafloor. I'll show you some video of that. And they provide the main power to the smaller work areas, and I'll show you that. To get to the access of smaller work areas, most of this infrastructure was built and designed by the UW Applied Physics Lab. So the nice thing about that is things like the junction boxes, which are really the substations in the main experimental sites that the instruments and platforms connect to. Because APL built them, they're easy to modify for specific needs of PIs. There's 18 of those that are installed. We first installed them in 2014. We've never had any problems with them, and all of them are operational. Another very cool piece of infrastructure is we have 6 up to 2,700 meter tall moorings, and I'll show you some images of that. So 140, 150 instruments on the sea floor. A few of them are unconnected, things like water samplers, but the rest provide 24/7 data and two-way communication. The initial design since day one was planned so that it's highly expandable. We use very little of the data capabilities and have a lot of power available still. So this was constructed, it was a 5-year construction, and it was built on time and under budget and finished in 2014. And we're now in the 3rd year of operations and maintenance, and I'll talk a little bit about our cruise this coming summer. So yeah, as I just mentioned, I'll give an overview, and then Dana will talk about more of the details on the secondary infrastructure, different instrument testing integration, and then how we can support PIs. So this is the video. It's coming up in just a second. That is of the primary infrastructure installed on the seafloor. This is it was a great collaboration with LT Ameripro. This is one of the primary nodes. It's in shallow water, so it has a trawl-resistant frame. They're quite large pieces of infrastructure. Because of, to optimize the most efficient operations and maintenance, processes that we could. Almost everything is connected by wetmate connectors. Shown here, there's different ports. Each primary node has 5 science ports and expansion ports. This shows the ROV ROPOS connecting these, and what this means is that we can connect and disconnect the instrumentation without having to bring either the primary nodes or the secondary nodes off the seafloor. So it's a very efficient way to do operations. So there's 7 of these, 6 of them are fully outfitted, and we've had, since they were installed, we've had 0 problems with them. So again, they've been super high reliability. This is the secondary nodes. They were designed with a lot of input from ROPOS, the Canadian Scientific Foundation, and they installed all of our secondary infrastructure and did a year of operations and maintenance with us. So the nice thing about these is they're built, most of it's built by the Applied Physics Lab, and it has a latching mechanism that is an industry latch, so the vehicle can latch right into the secondary junction box, and it's very easy to get it through the seawater air interface. It's super safe, and you can it also allows you to put it very precisely on the seafloor. And this is one shown on axial seamount, about 1,500 meters water depth. You can see those orange handles are, again, the wetmate connectors, and that orange cable is extension cables that go out to the different instruments. Dana will go into more of the specifics about the secondary junction boxes, but basically we work with PIs to figure out what their requirements are for communications and bandwidth, and modify the junction boxes to accommodate those requirements. They can be, again, these are also designed to be expandable, so there's a port on each one, so we can daisy chain the junction boxes and expand the network quite easily. We do a lot of instrument tracking, both in terms of engineering data and the data people at Rutgers, where all the data go into, which is the Ocean Observatory's org data portal. They also are monitoring now data flowing through the system. Again, all of ours is in real time. And this just shows, as of September this year, all the green means that every single one of those platforms and sensors is all operational. So you can see, except for a couple instruments that are in black smokers, tough places to work in, we have a very good track record. We're also developing, or I should say the data portal folks at Rutgers have developed machine-to-machine interfaces or capabilities now, so PIs can access the data products in real time. We've had, so this last summer was our 3rd operations cruise, and this just shows you that we turn a ton of instruments and platforms. I think it's over 200 that are over 120 instruments usually that are picked up and put down on the seafloor. Most of the junction boxes are designed for at least 5 years of being on the seafloor. Again, we haven't had any trouble, but we do turn some of them for things when instruments become biofouled. We have 3 of the large shallow profilers. I'll show you that in a second. Some benthic experiment packages, which are in shallow water, and some deep profilers. We take PIs out on the ship with us, early career folks, and then through the UW educational program, we always take at least 20 undergraduates with us and grad students from across the U.S. We provide live streaming video of the operations and good communications through VoIP phones, so PIs, if they don't and can't be on the ship, have access to the data or the video in real time and can interact with us live when we're on the ship. The cruises are very different than science cruises. They're really an industry scale of operations. Unlike most science cruises where you want the vehicle to stay on the bottom the longest that you can typically, ours are just opposite. We get in and out of the water as fast as we can to get all the requirements for the switch outs done during the cruise. This just shows you the back deck of the Revell in 2017. you can see there's kind of a little bit of walking room between all the infrastructure. The instruments in the back, platforms in the back, the orange ones are components of the shallow profilers. And so we have a lot of work that goes in, typically led by Skip Denny in the Applied Physics Lab, of figuring out the deck loads, where everything goes, what the order is going to be installed in, and a lot of deck checkers of moving things around. So as I mentioned, the Canadian Scientific Submersible Facility ROPOS vehicle did the initial install and first year of operations. It was designed specifically for cable observatory work, and this shows it going in the water with the ability to lay cable. They laid over about 33,000 meters of cable, finished that in 2014, and we've never had a single problem with any cable that they installed. And the main things about this vehicle is it has heavy lift capabilities. So some of our packages are up to about 3,200 pounds, has a 4,000-pound lift capability. And then the National Science Foundation supported vehicle Jason, run out of Woods Hole Oceanographic Institution, is now taking over the operations. And we had our first O&M cruise in 2016 with them, and we'll use it again we used it in 2017, and we'll use that again in 2018. And it has pretty much the same capabilities as ROPOS, except for installing cables. So this is a deck layout. We provide these and talk about them with the PIs. But again, we have both weight considerations, power considerations, and then just some major deck layout. So as I'll mention later, we have 5 PI teams that have been awarded proposals from the National Science Foundation, industry, ONR, and Germany. And so we'll have a lot of calls with them coming up starting in January timeframe, and then a meeting where all the PIs come together to work out the order of operations. The other thing that we're acutely aware of is weather, and this is something that Skip Denny put together. We're able to, with what he's done in looking at wave conditions, weather conditions, we can plan out actually really remarkably well a couple, 2 to 3 days in advance. And so there's the way that we run these operations is one where there's a platform like a junction box underneath the vehicle, and that's shown below the dive index of 40 there. And then what those lines are showing is basically the increasingly bad or good weather coming through the system looking ahead, and then anything above the 40 is where Jason can dive but without a heavy platform underneath, and then that green line is no dive. And so we spend a lot of time working through this and talking with the ROV pilots, the leads, expedition leads, and captain to make sure, do the look-aheads. And that also means that we have the flexibility to drive from, say, near Newport to the volcano, which is about a 20-hour transit, to mitigate and most efficient operations in terms of running from the weather. Just a little bit, I'll show you some of the infrastructure that we have in place. There was about 80 researchers that were involved in the initial design of, in terms of the science, and that flowed down into the engineering requirements. And this is just the infrastructure, some of the science issues, studies, focuses of research off of Newport, Oregon, which goes from 80 meters for the cable, 80 meters down to 2,900 meters at the base of the subduction zone. It's a little bit of eye candy chart, but I like it because it shows both the uncabled and cabled infrastructure that we have out there right now. Oregon State University, in collaboration with Woods Hole, Oregon operates the uncabled infrastructure, so there's a series of moorings that have seafloor expressions and transmit their data via satellite, and then also the instruments are recovered. And there's also a series of 6 gliders that go off from Newport and then up to the Washington line off of Grays Harbor. And this shows the cable infrastructure as well, and the location of the 2 different kinds of moorings. One is the 2-legged mooring, and then the single cable deep profiler. There's really no place else in the world right now that has this amount of infrastructure providing data on a pretty important, very biologically productive area of the ocean. We have detailed bathymetry maps for all of the work sites. This just shows the Oregon offshore endurance site, and then the area at 2,900 meters for slope base. We have bathymetric resolutions for most areas of usually 5 meters at axial seamount. It's even better than that thanks to MBARI. And then we also have dive track lines and GIS that we can provide for anybody that's interested of where all of our infrastructure is. And again, it's updated every year after the field programs, and we have a database for that gets updated. We have three-dimensional drawings also for perspective drawings that shows all the infrastructure and track, have a pretty detailed asset tracking management system, so we keep track of individual cables as well as the sensors, everything on the seafloor and in the water column. This is not the greatest in terms of clarity image, but these are called functional block diagrams. They're engineering diagrams that detail from an individual connector and port on the secondary and primary infrastructure to the instruments as well as the cables, and this is part of the asset management. But they provide, I think, some very useful information to people that want to add on to the array by showing everything that's at one site, and it includes kinds of connectors as well as cable lengths. And we'll zoom into the one at slope base, which is a medium power junction box. And this is a blow up of that area, so it shows dry mate connectors as well as wet mate connectors, the kinds of cables, and then the instruments that are down there, as well as the abbreviations or identifiers for each of the instruments that flow down into the data portal for access of instruments. Just to zoom in a little bit about the underwater moorings, so these are designed and built by the Applied Physics Lab. The shallow profiler moorings, again, there's really nothing like them in the world's oceans right now. They include a platform at 200 meters water depth. There's 3 of them out there on the array, one at the Oregon offshore site, one at slope base, and one out at axial seamount. They have a stationary platform that has a set of instruments, and then the really novel aspect of this is there's a winch underwater profiler with a science pod that has makes 9 trips a day and goes up and down to the water column. These have been remarkably successful. They have a really good history. I think we're probably up to 15,000 profiles. It runs 9 times a day, and I'll show you that in just a sec, a little bit of that. Again, we have the functional block diagrams. This just shows the instruments on the stationary platform. That's the pod off to the right. And this, just as a reminder, this probably has at least 30 to 40% expansion capabilities, more depending on what the power requirements are for the instruments that PIs would want to add on to this. These are designed with operation efficiency in mind again, and so they are recoverable and are installed by an ROV, each of those 2 platforms. It's a very efficient operation. It takes about a day to turn both the stationary platform and the shallow profiler. We've done it 4 years in a row now. And the kind of power requirements and again, these can be adjusted, the ports can be adjusted for PI instruments, but it makes 9 times a day right now. It has a mission execution plan, so there's no human in the loop. And it has the capability it stops on the downwards path, will take measurements, things like CO2, or when there's instruments that have pumps, so that you don't get a kind of a smeared out signal. It'll stop, make those measurements, and then go on its way again, and then go down in the docking station. And again, these have been really, really great workhorses. We haven't had too many problems with it at all. Because of the cable, every instrument is basically full out in terms of its bandwidth and what it's sending to shore. So this just shows you one of the oxygen and temperature profiles off the endurance array, and then to the left is the kinds of sensors that we have on the platform interface controller and the winch shallow profiler right now. And again, these are turned annually. Zooming into axial volcano to give you some insight onto the seafloor infrastructure. This was chosen again by the community because it's the largest and most active volcano on the Juan de Fuca Ridge. It erupted in 1998, 2011, and 2015. 2 days after, there was a large workshop here with an international group of scientists trying to plan out how to respond and when the next eruption will occur, and it happened 2 days after that. There's a pretty decent array of infrastructure on the summit of the volcano. It's a little over 300 miles offshore, 1,500 meters water depth. You can see the primary node PN3B there on the summit. It's out of the main area of volcanism to keep it safe. And then we have a series of extension cables and junction boxes to reach the experimental sites. There's a nice diverse array of geophysical instruments, things like hydrophones, broadband, and short period seismometers, to look at how the volcano's behaving, how melt migrates in the seafloor. In the 2015 eruption, in a single day, it tracked over 8,000 earthquakes, and the seafloor fell about 2.4 meters. And that resulted in an eruption to the north of a flow that was 127 meters thick. There's two main hydrothermal sites that are instrumented, Ashes and International. And there's an array of instruments, so we have things like digital still and HD camera, mass spectrometer to get volatiles, and then instruments that go right inside the black smoker chimneys, temperature resistivity to look at boiling, and pH hydrogen sulfide temperature sensors. And then we have another instrument that sucks in hydrothermal fluid and traps the fluid, preserves the fluid that we recover for later for chemical analysis, and also another system that sucks in the fluid, and again we're monitoring temperature during that time period, preserves the microbial DNA, and those are recovered annually to look at the change of microbial communities over time with co-registered with fluid chemistry and temperature, as well as seismic activity. So this has been a very successful, we've had good history with most of the instruments. I wanted to highlight that we have core instruments, which are those in white, and that means that NSF is committed to maintain and operate those for a 25-year period, contingent on whatever the DC budget's doing at the time. But and then, so those are all core instruments, and then we have the PI instruments, which are those that are funded by either National Science Foundation, industry, ONR, or by international collaborations. Our first NSF-funded collaboration was Bill Chadwick. He got funds to install another bottom pressure tilt and current meter instrument, and that was done in 2017. And then this next summer, I'll summarize on an ending slide the PIs and all the instruments going in next year, but there's a power generation system in Ashes, a plume sonar to look at diffuse flow, look at heat flux in the Ashes hydrothermal field, and then two different kinds of geophysical instruments to look at geodynamics, seafloor inflation, deflation at axial seamount up at the central caldera, and I'll go into more detail there. So this is the kind of bathymetry that we have. This is, we have, thanks to Mbari now, we have sub-meter resolution bathymetry, and this shows the layout of the Ashes hydrothermal field. So very good database that people can have when planning their experimental sites. These are just some of the questions that the community had laid out, and then the individual sensors that we have located in this one study area. We also have two of the sites, photomosaics at Hydrate Ridge, which is a methane seep site. We have very high resolution photomosaics of the entire seep site where you can see individual animals. And then this is the Ashes vent field. All those white areas are where there's hydrothermal fluids coming out of the seafloor and microbial communities and tuberums within those cracks. So again, these have been very useful for PIs to plan out their experiments. This is just some imagery that's come in from the high definition camera. It runs 3 times a day, every 3 hours, and again sends HD imagery live. This is a photo mosaic. It goes over the entire chimney at the same views during each cycle, and then it can be photo mosaic at very high resolution, and these frame grabs off to the right show tuberms and limpets and bacteria that are coating the tuberms. So again, these are providing an amazing imagery and data on how these chimneys evolve over time, both with respect to sulfide growth as well as the communities that colonize these chimneys. So before and after we install instruments, we take high-resolution photographs as well as video, and those are all available to the community, as well as summaries. They're kind of like the Reader's Digest version of dives, showing all the key operations, and we can provide those to interested users. We also have the ability to take verification samples in terms of volatiles, gas types, niskins on the vehicle, and we work with the PIs to make sure that we get done what they need. So next year, this coming summer, we have 47 days. Go through some of the instruments that will turn, and then a listing of the NSF and other funded projects to date. So we have 4 instruments that are funded by Germany that will be installed at Southern Hydrate Ridge, the power generation system by ONR, the COVIS diffuse vent imager at ASHES, and then 3 of the geophysical arrays or sensors that will be out there. This summer we'll either recover or keep the Bill Chadwick sensors out there. We're working through a process on how instruments might become core, and there's a request into NSF for that now. Finally, the cruise data and instrument data. This is the link to the oceanobservatories.org website, which is the main program website that provides where you can access information about all the operations, the instruments, and then a link to the data portal where you can access the data. And then a link to our site, which is the educational site that provides a lot of the site imagery, video, and summaries of all the dives. So we've gone through the kind of the introduction now, and then Dana will talk more about how the necessary information and how we plan out PI instruments. I guess we can take, before Dana goes, are there any questions out there right now that we can also answer them at the end of this? Okay, go ahead, Dana.
Okay, thanks, Deb. Next slide. So now we're going to take a deep dive into infrastructure. The pictures aren't as pretty, but hopefully a little bit of information in them. So I'll go over the general architecture, what the secondary nodes are, what they look like, and how to interface to them, and in addition to the details of the voltages and communications that they support. Then we'll talk a little bit about instrument testing, how we get instruments integrated in with the infrastructure, some lessons learned, and show you some photos of our facilities and support that we can do from here. Okay. So the cable array architecture, kind of some key points to keep in mind is that each instrument port can be assigned and configured with a unique IP address or multiple unique IP addresses. All data is networked back to shore in real time, so we have full and complete interaction with the systems in the water at all times. We can control power also instrument by instrument from shore. So we collect and monitor the data for each instrument port, including things like electrical current, voltage, and whether there's ground fault issues on that port. There's GPS-based timing available, and so we provide those signals at each instrument port. And also, we use ROV wet mate connectors, as Deb mentioned, to allow annual maintenance on the instruments and the infrastructure that allows us to take pieces and recover those without recovering the whole. Not sure where that static is coming from. Hopefully that's not on you're not getting too much of that on the line. So the cabled array architecture basically runs from the shore out through the primary infrastructure that includes the backbone cables, primary nodes that Deb showed you some nice video of those, and those push out into junction boxes. And so we have a few flavors of junction boxes on the seafloor, and those are what interface directly with the instrumentation. So a medium power junction box can support up to 8 instruments, and as Deb said, that there's ports for expansion, so we can daisy chain those. We can put some lower power junction boxes on that support some lower power instruments, again up to 8 instruments. So next slide. Okay. So the secondary nodes, and I'm focusing on the junction boxes, but most of this information also applies to the platforms that you saw on the moorings as well. So junction boxes are the main interface between the cabled array and the instruments. I like to think of them as power strips on the seafloor for instruments. Each one supports, again, up to 8 instruments per junction box. The instrument ports are pre-configured at the build time, so we can set the voltage, power, communication, and the connector type that's used on that port. And what that means is that if you are going to add an instrument to the cable, we would work with you in advance to understand how we're going to power and talk to that instrument and make sure that we have a port that supports that specific configuration. Connections to the instruments can be made either with wet mate connectors or potentially they can be dry mated to a junction box, but that means that instrument has to ride up and down with the junction box itself. So another thing to keep in mind on the cabled array is that the length of the cable dictates how much power is available. So for instruments that are close to either their secondary nodes and secondary nodes that are closer to primary nodes have basically unlimited power and bandwidth options. The longer the cable runs get, the more voltage drop we get. So there's less power and bandwidth available. So this is just a photo of one of our engineers, Mike Harrington, testing an open frame secondary node. So you can see there's a pile of boards in there that are instrument ports as well as a node controller that allows us to connect to and talk to the node from shore, voltage converters, so all your standard stuff, Ethernet switch. Those two big orange cables on the bottom have both power and fiber optics. So this is a medium power junction box, so there's literally data at the speed of light traveling to and from this node while it's deployed. So you saw the picture of ROV deploying a cable spool. So this is what the ROV looks like connected up to one of the junction boxes. Next slide. And so that's a junction box on the seafloor. The one thing I'll point to is in the middle, on the top of the junction box, there's 2 latches. Those are called Perry-Slingsby latches, and that's what allows the ROV to latch into the junction box. It can support several thousand pounds. That kind of latching can be used for instrument packages as well. We can provide details on how to construct a latch that's compatible with that system. Okay. So as far as interfacing to a junction box, there's multiple communications options. So Ethernet, RS-232, we can make RTS and CPS lines available, RS-45, so I think these are now called EIA, but I think most of us recognize them as RS, RS-422. So for long runs of cable, we recommend using a differential signal like 485 or 422, either in full or half duplex. We've had some success. So the 422, we would want to do some extra testing to make sure we have all the terminations correct on those communications. Fine. So our standard voltages available over the instrument port are 48 volts, 24 volts, and 12 volts. Although you can talk to us if you have a custom requirement, and we'll see what we can do. Power, again, standard power at each port is either a 50-watt or a 200-watt converter. There's no 200-watt options available on low power junction boxes. Those are available on medium power junction boxes only. So timing signals, there's a number of ways to make sure that each deployed instrument has a sense of accurate time. All timing is based on shore-based GPS systems from the shore station in Pacific City, Oregon. We can support NTP or precision time protocols, or PTPs for Ethernet instruments. Any serial instrumentation is going to have its data timestamped in the junction box to about a 10 millisecond accuracy. So it just depends on how accurate that's the time that that data packet reaches the junction box, and then that data is all pushed ashore. We also have 1 pulse per second signals and NMEA time strings that we can push to instruments on the cable. So connector options, primarily new seafloor instruments use ROV wet mate connectors, which you see on the left-hand side. So these plug into a connector panel on the junction box frame. Good thing about those is we don't have to recover the node to either connect or disconnect the instrument. It is possible to do dry mates to the junction box, but again, that instrument would then be deployed with the junction box and would not be recovered until the junction box itself is recovered. Okay, fine. Standard 12-pin connections, the MHDXL is the impulse connector, and so we support pinouts for each of the different interface options. And so again, back to cable lengths. So the cable, or the communication protocol and the cable lengths are kind of important. So if you, again, using the maps that Deb showed, how we have the site maps, so if you know that you need to be, let's say, 50 meters away from a junction box in order to be at the study site, you'd want to have some excess cable to make sure that you can get your instrument there. So you might want to plan for a 70, 100 meter cable. That's about the maximum, about 70 meters is the maximum for Ethernet. For RS-232, it's a bit shorter than that. We wouldn't recommend going longer than about a 10-meter cable. If we need to make a longer cable run from a junction box, we would recommend RS-422 or 485. We have had success operating short period seismometers on over 1,200-meter cables at 38.4 kilobits per second. So for wet mate cables, Teledyne ODI is the provider of those, and we can, anyone who is going to attach to a junction box, we will provide part numbers that can be shared with Teledyne, so you can get up-to-date quotes on those. So this is, sorry about the small font, but just generally the process of getting a cable onto or getting a new instrument onto the cabled array. So it starts out with scoping and proposals. We want to talk to you early and often if you go through this process to make sure that the connection is feasible, that we can power your instrument properly and communicate with it. and have options for controlling it and collecting data once it's deployed. So typically there's an upfront scoping meeting with the MIO stands for Marine Integration, no, what are we? Marine Implementing Organization. And so that would be us here at UW. We would have a form for you to fill out just to give us general information about what your instrument's supposed to do, and then we could work through that with you to make sure that it's feasible to connect it to the cable. Once that happens, your proposal goes in, gets approved, and then comes the fun part, is the build, development, and integration. And so again, we'd like to be involved as early as possible in that process. And so we'll invite you out at least 3 months before the deployment to complete a series of integration tests at the UW facilities, and then finalize the deployment and operations plans. And then once the instrument is installed on the cabled array, then there's ongoing operation. And again, we'll be here to support you through that as well. So switching gears a little bit to our instrument testing, we have a few objectives when it comes to making sure that an instrument will play well on the cable, and that the cabled infrastructure will be able to properly operate that instrument. So the first thing is just to verify that instruments are complete, that they're gonna be robust, reliable, and functional. We do not do calibration checks on instruments, so whether it's good at testing or at measuring what it's supposed to measure, that's up to you. So the second is just to verify that the instrument can function as an integrated part of the cabled array, so that it has the correct interfaces and that it won't be susceptible to or cause interference to other instruments on the array. So far, over 30 different types of instruments have been connected to the cabled array, and all of those types are working and collecting data. So that's just a short list of the instruments so far that we've connected to the cable. So the test flow, each instrument, when it comes in, goes through a physical inspection, and so this has happened to all instruments on the cable array, including the core infrastructure, and generally this is what we would do for integrating a PI instrument as well. So physical inspection, followed by just powering it up, does it work? All instruments, or all pressure housings undergo a pressure test to their, at least to their deployed depth. Electrical characterization, this is just understanding whether there's spikes when it turns on, whether there's current spikes. So we understand how it works, or while it's sampling, what we can expect out of that instrument. We check all instrumentation for electrical isolation, so we want to see at least 10 megohm, if not more, at a 50 volt at 50 volts applied on all pin signals and power and ground. Make sure instruments have been run an adequate amount of time to avoid any failures due to just early or poor components. And then run through a full set of functionality, make sure all of the things that the instrument has to do on the cable that it's capable of doing. And once that happens, then it's time to plug it into a secondary node. So what have we learned so far through this process? Quite a bit. I think most people who have put anything in the water know that material selection is important. You see there on the right-hand side an image of a housing that was an anodized aluminum housing after 1 year. Luckily it didn't leak, but there were some pretty nasty pitting, some of it close to an O-ring. So, second is always test for electrical isolation. Even with commercial systems, we often find that a internal wire can get pinched up against a housing in a way that wasn't supposed to, and that can cause currents to flow into the seawater around the instrument, and so that's bad for a couple reasons. One, because it can cause early degradation to that system, corrosion, and it can also interfere with measurements of surrounding systems. The third is design with deployment and recovery in mind. So a lot of times we think about what we're measuring, and then it's kind of a last minute, well, how are we going to get this to the seafloor, and then how are we going to get it back up? Keeping in mind that it's approximately $1 a second while an ROV is at work off a research vessel, it pays to spend a little bit of time up front thinking about how we're going to deploy and recover, and we can work through options as well. Next one is just double checking connector pinouts. A number of times we've gotten TX and RX slips. I've stopped counting. Needing to understand electrical transients and noise sensitivities, so especially instruments that have large inrush currents. We've found a few even commercial systems, again, that typically run on batteries, so when we've put them on cable, we'll find that they have sleep-wake cycles that involve large current transients, so it's important that we understand and that we can accommodate those with the cabled infrastructure. Cable length is another important thing to understand, that communication signals and voltages, as cables get longer, they change, the voltage drops and the drop out of communication signals if they're on too long of a cable. So in terms of interfacing and commanding and controlling instruments, menu-driven user interfaces can be very difficult when we're trying to automate a process. So if you want a system to take a sample once an hour, and you have to go through a menu-driven process to do that, then somebody's going to be awake 24 hours a day. So command line interfaces are useful, and then lastly, avoid at all costs ways to get into unrecoverable states through the console. So things where you've got to reach in and reconnect a battery inside a pressure housing. Obviously, that's not something we can do once the system's been deployed, or any special keystrokes that will erase firmware, things like that.
It happens.
Yeah. So just to wrap things up a little bit about our testing facilities here, we have a test lab in Ben Hall on the UW campus. We have saltwater tank, power supplies, plenty of insulation resistance, test meters, test freezer. We also have space in a nearby warehouse a few miles away where we'll likely do the majority of our PI instrument testing. In the Ocean Sciences building, there's a saltwater test tank, as well as a pressure test vessel that can accommodate up to 24-inch diameters. It's a fairly hefty size. Okay. We have portable test equipment, so we can bring basically what amounts to a secondary node to say the test tanks, and so we have ways to connect two instruments, make it look like they're on a cabled array interface, and then a few benchtop portable instrument ports, which are nice for comms testing. And then if you find that you've got a great system sitting in front of you but have no idea how to package it for deployment in the ocean or connect it up to a cable, happy to help you through that process with mechanical engineering, electrical engineering, any kind of component integration, firmware, software, obviously pressure tank testing, saltwater testing, and we have a clean room available for assembly that we use for all of our secondary nodes close up here. So if you've seen this and you want more information, you can contact us at this ooicable@uw.edu, or as I think Brian mentioned at the beginning, sign up for a consultation through the website. So I think with that, we're going to open it up to questions.
Yes, that ends our prepared material. So if there's any questions from anyone, we'd like to help answer. So just as a test, can everyone hear us okay?
Are you muted somehow?
Dennis, can you hear us?
Hey, Lisa, can you hear us out there?
Yeah.
Okay, thank you. We hope we weren't talking to ourselves.
Great. If there's no questions from the members, if there's additional information or if you'd like to set up a one-on-one consultation with the cable team, you can sign up through the website or an email to one of us. That'd be great. And thank you again for joining us today. And we look forward to potentially working with you in the future. Thank you very much.
Thanks, guys.
Thanks.